So today we're going to be talking about trees. I guess I already said this word once when I told you like every data structure we're going to learn in this class. I had a slide on that, right? But it's been a while. Let us begin with a new topic. It's very exciting. It's kind of like a linked list, but cooler because you got more pointers involved. So it's going to be wonderful. Okay. So I do have some bad news for you if you don't like linked lists or pointers. Surely there's nothing that could be worse than those, right? Right? Enter binary trees. So, all right, let's talk about these guys. So a tree is another kind of data structure. It's got a cute name. It's got a cute little metaphor. It looks kind of like the roots of a tree. This is a drawing of a tree. Looks like the roots of a tree, or if you turn it upside down, it is the branches of a tree. Whatever you want to think about. So yeah, a tree is another data structure, but it has nodes, just like linked lists. So we still call the things where we're storing data in the trees, we still call them nodes, but instead of like a next pointer, there's going to be pointers to people below you, which are your children. It's like a family tree. You can think of it that way as well. So it's kind of cute. You cannot have any duplicates. You can't like wrap back around the tree or do something weird like that. It's always you're the great great grandparent, and you have like a left child or a right child or a middle child, something like that. And you can always go down to lower levels, like you can go down to your children, but like your children can't go back up to their grandparent or something weird like that, or you can't go to the side. Like there's other kinds of trees, but not the kinds we're going to learn about that do that. All right, so no duplicated pointers. There's only one way to get somewhere. All right, starting from the thing at the top, which is where you begin, right? It's called the root of your tree. That's the thing at the top. And so here's, I don't know, where the roots begin. And so here's the rest of the tree up here or something. But this is called the root of your tree. And that's what you're going to pass around as you give somebody your tree. As you give somebody your tree, you pass around the root because from the root you can get everywhere. Right? Just like when you pass around a linked list to like a recursive function or something, you pass around the first node because from the first node you can get everywhere. So this is the same idea here. Okay, so there's a root pointer. We are not going to really care about these kinds of trees with maybe like middle children and things like that. We're going to care about binary trees, which are trees with at most 2 pointers coming out down on the family tree line. Okay, so 2 pointers at most coming out of you. Like here's the root. You'd have like a left child and a right child only. Sometimes they don't exist. Like eventually you're going to get down to the lowest level, and like maybe this node right here has a right child but not a left child, stuff like that. And then once you get down to the very bottom, like the most recently born children or something, there's nothing coming out of them. There's no left or right pointers, no children yet, and so we can mark that as null. We will get there. Okay, so yeah, does that make enough sense so far? Just like we got nodes, 2 pointers coming out of each of them, and we'll think about it in this kind of diagrammatic way. Cool. Yeah, so let me draw some binary trees this time. Let's draw like a tree that holds some integers, like maybe at the root we've got a 1 node, and then I don't know, this could be a 3 node, a 5 node. So you can hold on to numbers as long as you like remember where they are, like go left, go right, stuff like that. 7, you can find your way around. Maybe 42 goes here. So there's that. You've kind of used trees diagrammatically before, like in a CSCI 40 class. You're like, all right, how do programs execute so we can branch off? It's kind of like drawing a tree, isn't it? So like if x is a true variable, do one thing. If x is a false variable, do another thing, or based on y. So like that is technically a binary tree. Like, all right, based on x, if it's true, thing x. If it's true, or if it's false, I'll do one thing or another thing. Like if it's true, I'll launch a missile or something. If it's false, I'll just sit here and make coffee. Yay. So like that's a binary tree technically, right? And programming languages very often can be turned into maybe not always binary trees, but a tree-like data structure. So like let's say you have, and you'll study this if you take a compilers class one day, and I highly encourage it because it combines all of the knowledge that you'll ever have learned in computer science. Like let's say you have this code, like while 2 plus 2 or something. I don't know. That's your condition. That's your condition. As long as that's true, don't worry that it's just a math. Do like statement 1 followed by statement 2 semicolon. It's like if that's a loop, you can turn that into a tree, and that's how that's what's happening when you are compiling your code. It is really getting turned into a tree so that the compiler can figure out what you're trying to do and emit machine code, something at a lower level. So all right, how does this get turned into a tree? Well, it's a while statement, a while loop. And so you have a node that marks that, and then all right, what does a while statement, a while loop need? It needs a condition part and it needs a body part, right? It needs those things. And so I don't know, what's the condition? 2 plus 2 for fun. Well, that's just a plus operation on 2 and 2, isn't it? It's you can turn that into that kind of thing. And then the body is 2 statements, which you can then whatever they were, you could build up their trees, but it's statement 1, and then maybe go to the right for order purposes, then statement 2 after that. So you can turn code into trees, and that is a very common thing. It's called a syntax tree, and you'll need that one day. So trees are everywhere. They're very important, and we better learn about them. So yeah, I think I've shown you enough. I'd like you to think about this. So please try, if you can, get into a little peer instruction group, say hello. I'll start the written nice page just in case you'd like to tell me. I highly encourage you to submit something. But let's see if you can figure out, I'll clear this out. Let's see if you can figure out what is the struct definition for a tree node, all right? Write a definition for a tree node struct that represents a single node of a tree, and let's say that instead of holding numbers or code, we're going to hold characters. The tree is going to hold character data, and so let's say you want to be able to represent this kind of tree. Oops. Boop, boop. So at most 2 children, and let's say you can store an A character here, B, C, you can put data at each node, and that data is a character. All right, so think about zoom in on any particular node, that one, that one, that one. What does it need to be represented? Does that question make sense? It's very similar to a linked list node. What will you call it? Give it names, yeah? So give that a try, and then we'll come back and we'll show you my definition. I would love to know what that is. Kind of looks like what I have. Another minute or so. Or no, I'll give you 2 minutes. I want you to think about it. We're still talking. Another minute or so. So what do you need? How did you know? Like for lists, you need a data and next, right? What about a type symbol? All right. Give me a second here. Oh, thank goodness. Okay, that is what I wanted to know. All right. So let's see what we're thinking. Press submit if you have not yet. Let's see. Look at us. Nice. We notice that we're going to need some tree node stars. Dun dun dun. Very nice. Character data. Somebody's thinking about parents, but I did not draw any parent pointers yet. You've been reading ahead, maybe. But yeah, that's kind of what it's going to be, given what I drew. Like, we're going to need a left child, a right child. They're going to be tree node stars, if we're calling this thing tree node. They're going to be pointers to more tree nodes, and then a character for data. So good job. Very nice. Questions about that? I'll write it out, but it seems to be making sense in our minds. What did I want? I want it to go here. All right, so let's say we've got struct tree node. Need that for sure. And then, all right, what's going inside of this? We've got, at every node, we got characters. So I'll call that character data. And then we've got pointers, right? Pointers to the left and right children. That's the names. And so those are going to be tree node stars. They're pointers to other tree nodes, just like linked list. Next was a pointer to another list node. So I'll call it left and right. That's just the canonical name for it. Tree node. That is not legible. Tree node star right. And that's how you can move around. That's pretty nice. And then if there's nowhere to go, just like for this one, you can imagine that there's going to be null pointers for the left and right children there. That's how you know not to go down any further. Yeah. So yeah, that's good. Does that make sense to us? Look at us. Nice. So yeah, here's the idea. And you could go further. You could talk about a parent pointer as well. We'll get to that. So okay. Here's the one that we were going to use in like a lab. We are going to include the third one. So got a left child, potentially your left child, right child, potentially your right child, null. It could be a pointer, right? It's a pointer, so it could be null. And we're also going to worry about who's above us so that we can come back if we need to. So yeah, let me draw some, like a sample tree. Here's tree node with A. Then we can have B and C. and then we can have D, beautiful, and we can mark the fact that like there's no right child of B by setting B's right to null, C's left to null, C's right to null. So that's a thing. And then we can also store parent pointers. So parent pointers look like this. Let's see. How do I want to do this? Dun, dun, dun. Yeah, let's forget about the parent for a second. So like think about it like this. So A has two children, B and C. That's the terminology, right? So B and C, just to mark it up, B and C are the children of A. And then these null pointers are going to mark the fact that you've got nothing below you. They're like the bottom of the tree. So you're going to say null pointer all day long down there. Null pointers mark. It's supposed to be an M. Mark the bottom of the tree. Okay. And then A is the root. A is the root of the tree. It's the tippy top. There's nobody above it. The root of the hierarchy. So A is the root of the tree, we say. Root of the tree. And it's also, though, you can think about it like A, B, and C are its children, so A is the parent of B and C. Yeah? So A is the parent. So and the parent. So you can mark that with pointers if you would like. And the parent of B and C. There's an A of B and C. There it goes. And so you can store that pointer like this. And so at every node, you have a parent pointer. So D, for example, D's parent is B. You can have that going on. B's parent is A. C's parent is A. All right? And so for parent pointers, you can have duplicates because like your two children have you as your parent. It's going to have the same pointer there. Who's the parent of A? Nobody. So we should use null again, shouldn't we? Just like you can't go down any further with child pointers, left and right. You can't go up any further with parent pointers once you're at the root. All right, it's kind of the opposite of the bottom there. So let's see here. Am I gonna say that term eventually? We'll get to that slide, but when you get down to the furthest end, we call somebody who does not have any children a leaf of the tree. So that's very cute. Lots of metaphors. So A is the root, like C is a leaf, D is a leaf. I'll have a slide on that. But yeah, I think that's all that I wanted to say about terminology, how you might code it up, where the pointers are going to go. Questions about this? You see how you could build that tree maybe? All right, so let's go to code now. Let's make a simple tree that holds, binary tree that holds integer data. And I think we're just gonna, do I want to deal with parent pointers? Yeah, why not? So I'll do that. And so we've got this going on right here. This is the tree I would like to make, 42, 3, 4, and 7, in that kind of way, all right, with null pointers to mean like, all right, 3 has nobody below it, okay? And so 42 is going to be the root node. It's going to have children, 3 and 4. 4's left child is the 7 node. That's how you can kind of explain it in on paper. 42 is going to be the root, so I'm going to have a root pointer sitting right there. Root. Okay, that's what's going to happen. And just remember, if there's no left or right, if there's some child that does not exist, like 4 has a left child but not a right child, you're going to mark that right pointer as null. All right, that's how that's going to work. Same with parent pointers. Every node always has a parent pointer unless you're the root. If you're the root, then there is nobody above you. All right, and then I'll show you how to like go through the tree and print out starting from the root node, because that's all you get usually. You're starting with the root, and that's the only window into the tree you have. How do you get to like all this data that we've put inside of it? So that's what I'll show you. Okay, so let us copy and paste this if we can to save me typing. I'll call this tree examples. Does it paste properly? It looks like it did. Nice. Okay, so I'm going to make a node on the heap, just like for linked lists. We're going to make these things on the heap. I'm going to make a node on the heap for every real node in this tree. So 1, 2, 3, 4 nodes total, right? So I'm going to make a few tree nodes on the heap. Tree node star 42 equals new node, or sorry, new tree node. And then I'm going to do that 3 more times for all the other things in this tree. I'm going to have a 3, a 4, and a 7. 3, 4, 7. All right, so I got all those nodes, and we can set their data, right? 42's data is going to be equal to, oh, I'm using ints, aren't I? Not char data, but int data this time. 42's data is going to be 42, 3, 4, and 7 similarly. All right, so I've set the data of the nodes, but these left, right, and parent pointers are garbage right now, and I better take care of those too. Okay, so who is the left of 42? 3. Who is the right of 42? 4. So we're going to set up those pointers. So 42, it has a left child, and that left child, the address of it is whatever is sitting in 3, right? Because 3 is a pointer onto the heap to that new tree node that is holding 3. That's how you set it up. All right, so just like lists, 42's left is 3, 42's right is going to be 4, the 4 node. Does that make sense what I'm doing so far? You see how it's similar to lists? All right, and then, okay, let's work on 3. 3 has nothing. 3 has no children, so its left and right will be null. So 3's left is null, and so is its right. And then 4's left is 7. 4's right is null. And then like that. And then 7, just like 3, has nothing below it. So no left, no right. We better mark that. Okay, and so that's the children, the left and rights of everybody set up properly. We still good? See how it corresponds? Here's the definition of a tree node right here. Left, right, parent. We still need to set the parents, of course. So let's do that. So, okay, we've got 42 has no parent. It is the root of the tree. So 42, its parent, we mark as null. There's nobody. And everybody else, though, has a parent. 3's parent is 42. What else? 4's parent is also 42. And 7's parent is 4. And that's pretty much the tree. Made the nodes on the heap, of course. And we set all the pointers. Does that make enough sense so far? Any questions about that? So usually you're not going to, like, somebody's giving you a tree, they've already done this for you. They're going to give you a pointer to the root of that tree. And so let's make a root variable that points to that 42 node. So tree node star root equals 42. And that's kind of all you get usually. Somebody just gives you that. You got to find whatever you need to find through that. Okay? So, yeah, that's kind of the setup. And that's how we made the tree. I think that is all that I wanted to say. Are we ready to print out the tree using only the root? So if I want the 42 starting from root, I can just say root's data, right? Because it's living there. It's fine. So see out root data. That'll give me my 42. If I want the 3, that is starting from the root. Root, go left, get the data there. Does that make sense? That's going to be root's left's data. Every time you follow an arrow in a picture, it's you dereferencing a pointer, right? Or using the arrow operator. So root takes you here. Left takes you here. And at that note, get its data. So that kind of makes sense. That's what I did there. That'll give me the 3. For similar reasons, root's right's data will give me the 4. And then to get the 7 is going to be root's right's left's data. Are you following that? It's a little weird. So go right, then go left, then get the data. And there they all are. Ta-da! Any questions about that now that we've seen it working? Does it make enough sense? Like following all these arrows? This is a great example for you guys to try. Like try to figure out like why is this doing the right thing? If the arrow is confusing to you, turn this into the dereference and the dot, because that's what it is, right? It's dereferencing the thing before it and doing a dot on the dereferenced thing. Okay. But yeah, that's the example. I think that's what I wanted to say. Any questions before I go to something else? This is fun stuff. All right. Here are some terms, some of which I have already said. Terminology on trees. This is like generic trees. For us, we have binary trees, only 2 children at most, but in general, a tree could have multiple children, more than just 2. So yeah, we call the links between nodes and their children, or also parents, we call those edges, because that's where you can move around. So some languages don't have like concepts of pointers, and so you think of it as just like a little line that you're following. You're walking across the line. It's called an edge in math, at least. A node without any children is called a leaf. All right, so like H and I are leaves, D is a leaf, B is a leaf, E, F, and G are leaves. Okay, so those are called leaves, which is cute. An internal node is just like not a leaf. It has 1 child at least. So like R is an internal node. Where's one with just 1 child? I don't see any. That's kind of funny. So like, oh, there we go. A is an internal node. It has 1 child. Doesn't have to have both. It's fine. The parent is whoever's above you. Like you are its child, they are your parent. So for example, Q is the parent of A, something like that. The root is the person at the very tippy top. And then we can talk about like how deep down does the tree go. So we can talk about how deep a node is, because usually you're getting somewhere always from the root. You can count edges to get to somewhere. So for example, this A node, how deep is it in the tree? What is its depth? Well, to get from the root to it, we have to follow 1, 2 edges. All right, so that's going to mean it's going to have depth 2 for A. So A is depth 2 for that reason. Boop, follow 2 edges to get there from the root. So A has depth 2, and then like L is 1 down further. So L has depth 3. You're going to follow 3 edges to get to it. L has depth 3. All right. And yeah, you can talk about all the nodes at a certain depth. That's called a level. So level n is the set of nodes with level with the depth being n. So like here are all the nodes at level 0. There's only 1, right? What are all the nodes you can get to by following no edges at all? Just the root. So that's level 0. Here is level 1. All the nodes you can get by that have depth 1. This is level 2. So all those nodes share the same depth. And then you can talk about like how deep is the tree itself. We call that the height, though. So the height of the tree is like the max depth. Take every node, find the depth of it, take the maximum depth. So like maybe you got just one way down there. That would contribute to the height of the tree. Okay, so yeah, what is the maximum level that we can find here? 3, 4. So the height of this tree is 4. So height is 4 for this tree. But if I added another node right here, now it's 5. You see that? That's the thing. And so those are just terms. Yeah, are there any questions about that? You try. So, okay, here are some questions involving those terms I just said. See if you can figure them out. We can go back to the written nice page if you want. That would work for me. So here, if you're already on it, refresh it so that I can clear it out for us. And yeah, let's try this. So think about those ideas. Remember these terms. Help each other remember. Your neighbors sit next to you. But try to answer these 3 questions about this particular tree that I've taken It's so beautiful. I spent a long time making it so pretty. So try to write the height of the tree, find the leaf nodes. What are all the leaf nodes? The nodes that are leaves. Remember what that means. We can discuss that after it. And then which nodes are at level 3? There may be multiple. All right. So yeah, go and try that for a few minutes and write down your answers if you can. For all three questions. Remember that height and level involve the idea of depth. Involve the idea of depth. That is all right. Another few seconds. All right, that's my timer. Was that enough time? Think about this. So here, let's see. Let's see our thoughts. We think height is either 4 or 5. We're not sure. Looks like we're coming up with the same thoughts of what are leaves. And the nodes at level 3, well, it depends on if we thought the height was 4 or 5, I think. So yeah, let's see this. Let's figure it out. So the height of this tree is going to be the maximum depth that we're at of any node, and remembering that depth is the number of edges you have to follow on a path from the root, which means then that the level 0 would be the root. So it starts at 0, just like everything else in computer science. So it starts at 0, and that might answer things. So that means these nodes have depth 1. That's level 1. These nodes have depth 2. These nodes have depth 3. And these nodes have depth 4. So that means the height of the tree is 4 then. Does that make sense? It's going to be 4 for the height. The leaf nodes are all the ones that don't have any children. So that's going to be, we got D, C, G, H, and I. I think we all got those. So let me just circle those in a prettier way. D, C, G, H and I, those are our leaves. Going in some order. D, H, I, wrapping around GC. There are those, bless you. And then the nodes at level 3 then are all the ones with depth 3. That's F and G. Okay? Did that make sense? So starting at 0, that was the one thing that threw us off, I think. All right, so we're not done with terminology, sadly. So there's a bunch of different ways you can describe trees. There's a bunch of different nice properties that trees could have. Let me teach you some of them. So here is a, let's see, a full tree. Yeah, let me draw a full tree first. A full tree is one where every node is filled in or not filled in. Like either it's a leaf or it's got 2 children. If it can have anything at all, if it has a left child, it also has a right child. So this will be, here's an example of a full tree. So I must, if I give it a left child, better also give it a right child. Oops, so that's a full tree. All right. A complete tree is one where all of the levels, except for maybe the last, for a weird reason that we'll get to eventually, contain every node that it could. All right. The last level is special, and it must, if it's complete, it's okay for that last level to not be filled in fully. It's okay for like to have just one child come out of somebody, as long as all the nodes are filled in from left to right, which is a very weird thing to think about. So this technically also is a complete tree. All right. So let's just write that, full and complete. It's complete because all of the levels contain all possible nodes, except for maybe the last, right? There's all those, right? Have as many nodes as they can, except for maybe the last. And this last level is filled in from left to right. Does that make sense? If I were to add another node and keep it complete, it would lose fullness, but it would have to be this left child here. Does that make sense? It's very weird. I would keep it complete, but it would lose the fullness property at that point. I could not add this node, then it would lose fullness and completeness. All right, it's got to be from left to right in order. The next possible node, if you want to keep it complete, it's got to be that node. All right, which is weird. And so another idea is this one here. Boop. So here is a tree that's complete. To keep it complete, I got to fill it in like this. This one, then the left child here, that one. All right, so that is a complete tree. It is not full because this child doesn't have 2. This node does not have 2 children. It is itself a child, though, right? So that is a complete tree only, that one. Questions about that so far? Yes?
Is that only the lowest row for completeness?
Yes, the lowest row you think about from left to right, everybody else better be filled in completely. Okay? Yeah. So that is how that works. It's very odd, but we'll get to the reason why we care about that soon. Other questions? All right, a perfect tree is exactly what you would imagine it to be. Like everybody's filled in, and then we all cut off somewhere. All right, so all internal nodes have 2 children. All leaf nodes are at the same exact level. So for example, here is a perfect tree, an example of a perfect tree. Boop. As you would expect, that is beautiful, right? That is perfect. Another example of a perfect tree would be this one, right? Still perfect. Technically, this is also a perfect tree, right? Just the root node only. All leaf nodes are at the same level. The root is the leaf at this point. An interesting property arises when you think about perfect trees, like how many nodes must they have? We've got, this one has 1 node, this one has 3, this one has 7. Do you see a pattern? Yeah, good. Yeah, you see that? It's 2 to the something minus 1 to the n minus 1, where n is greater than or equal to 1. Interesting. So that's kind of cool. That's perfect. And a balanced tree, it's the last one I want to show on this slide. A balanced tree is just like one that's not really leaning too hard. Like I would consider all these trees so far to be balanced, but you can imagine one that's unbalanced. Excuse me. Thank you. So you got this one going. Let's say you're leaning real hard this way. That is very unbalanced, yeah? Unbalanced. So that's, you can kind of see, right? that would be, it's kind of, there's ways to measure balancedness, but I just want you to think of it intuitively for now. So yeah, that is some new terms. Do they make enough sense so far? You'll get practice with them. You'll read more about them. So here's, like, there's plenty of things I've shown you that motivate binary trees, but here's like another motivation. Like, it's really nice to have a balanced, kind of complete style tree, if not perfect tree, because if you got a bunch of stuff, right, you could have almost, you can have like 2 to the n things, and you've spread it out, so it's easy to get to each of those things pretty quickly. You'll have to go down like what? 2 levels. See that? To get to 2 to the 3 things. That's pretty powerful. That leads to logarithmic time, if you think about it hard, which is kind of nice. So let's you do that to get down real fast to where you need to go. For example, like Morse code is a good example of technically a binary tree secretly. Like you can have a dot or a dash, right, in Morse code, if you ever learned that. And that's just like a left or a right child, isn't it? And you can encode the alphabet in that way with a bunch of dots or dashes, and that ends up giving you essentially a balanced binary tree. And you can have the alphabet, and you can get to any letter you want to get to. Oh no, my PowerPoint has frozen. Hopefully it saved things. Is it done? Are we back? That was scary. Okay. We're good, I think. Drawing too much at once. Oh no, okay. I think I need to restart PowerPoint, guys. It is having fun today. So I wanted that line and that line. And then let's let it save and I'll come right back to it. Sorry. It could be Firefox's fault. Maybe I'm using too much RAM. Go away. Come back. So you see how, like, with all those dots and dashes, you can get down to where you want to get down really, really quickly. You got 26 letters of the alphabet. You only have to go 1, 2, 3, like 4 dots or dashes to get to everybody. That's pretty nice. With only 2 options, right? It's kind of like a binary search. You go left, you go right, you cut off half of your options. Does that make sense to you? That's kind of neat. If you make it balanced, at least. That's kind of neat. Okay? And so that leads to a new concept of a special kind of binary tree that's going to help us find things quickly with logarithmic time. Because again, you go left, you go right, you cut off half of the places you're looking into, half of your search space, half of your options. All right? So let us introduce now a binary search tree, BST for short. Oh, it legitimately took away, there it goes. Good old PowerPoint. All right, BST is short for binary search tree. And so what we're going to do next is we're going to use a binary tree in a special way. We're going to have to put things in an order that we understand, first of all. And then once we have that ordering, just like you need to sort stuff to get logarithmic time and then use binary search, we're going to turn that into a tree kind of form. Okay? That's what we're going to do. We're going to figure out how to order the nodes in our tree in a certain way so that we can cut off half of our search space and know exactly where something might be. All right? It's going to be great. So, yeah, a binary search tree is just a special kind of binary tree where we've got an order that's going on here. All right? So let me draw a binary search tree and explain why it's a binary search tree. So, boop. If I go left, I can put a 3 there. I can put something bigger over here, put a 10 there. If I go left here, I can put a 1. If I go right here, I can put a 4. It's bigger. If I go right here, I can put like a 42. It's bigger. So here's kind of the idea of a binary search tree. It's when you go left, something's smaller. When you go right, something's bigger. But it's a kind of a global idea of smaller or bigger. If I go left from the 5 node, and I go right from the 3 node, I better not put a 6 there. Because left of 5 should have meant that everything over there anywhere at all is smaller than 5. All right? So that's kind of what I mean by that, if that makes sense. So, yeah, every time you go left or right, the node there, the node that you find, is like it's another smaller place, first of all. So just like you can, remember like for linked lists when we were doing recursion, you can split up a list into like the first node and then the rest of the list. And like that's still a list if you give a pointer to the start here. You can think of the same thing for binary trees. You can say, if you go left from the 5 node, this is another tree. Do you see that? It's a completely new tree. We call that a subtree. You give somebody a pointer to that 3 node, they don't know anything about anybody above it. Like that is, for all intents and purposes, it's another tree. We call it a subtree of the bigger tree. So that's a subtree. This is a subtree. And of course, you got subtrees within subtrees. That's still a subtree. But what's going to go on for binary search trees is that for every node you're looking at, say the 5, for example, the value in it, the data in it, we call that the key of that node. The key is greater than every node in the left subtree and less than every node in the right subtree. So, all right, that means if I start at 5 and I go left, anywhere I could possibly go from then on better be smaller than 5. That's how we're going to encode this. And then if I start at the 5 node, I go right, anything in that subtree, anywhere that I could ever get to is going to be bigger than 5. That's how we're going to keep track of where we are, and that gives us some strong guarantees about where stuff could appear. See that? And then you want to save that property for every node. That works for every single node. Every node is its own little subtree, and it has the binary search tree property. Okay? So like if you're at the 3 node now, you know just by going left from 5 that everybody over there is less than 5. But now if you have 3, if you go left from 3, everything to the left must be smaller than 3 now. And 5. But I mean the 3 wins out. And then if you're over here, if you go right of 3, that means everything to the right must have been bigger than 3, but also less than 5. You see how you can really say where something is. If you have a tree that has this binary search tree property, you know exactly that the 4 must be there. So it's very easy to search for something. You see 5, like, okay, 4, if I'm looking for 4, it's smaller, so I'll go left. I see a 3, oh, okay, if I'm looking for a 4, it's bigger than the 3, so I'll go right. And that will lead you to it in logarithmic time if the tree is balanced. Cool. So, yeah, that's where we're going. Usually, it is strictly less than, strictly greater than. You don't usually have duplicates in a binary search tree, but you could have duplicates. You could just be like, everything to the left is less than or equal to. Just pick a side to have the equals to mark, whatever you want there. So, usually there's not going to be duplicates, though. So, yeah, let's see. Let's do this, essentially. Let's make a binary search tree and go from there. So, how do I want to do this? I need to draw more pictures. So here, let's steal this tree because I like this tree. Whee! I'll erase some stuff though. Boop. So there's my tree. Oh, no. Let's use the mouse. There we go. So let's let me erase the subtree stuff. Go away. Magic. Okay, so did I do that wrong? No, okay, we're good. So yeah, let's learn how to search through this. Let's say we've got this tree, this binary search tree, and we'd like to find something in it. So like usually when you're passing, like we want to make the function at the top there. Like you've got the root of your tree, somebody's passing that, like search. Here's your tree. You give the root to represent the entire tree. That's where you start always. And you give the key, right? That's the fancy term meaning a value inside of a node that you're looking for. So like I'm looking for a certain key in this tree, okay? And you're always starting from the root, and hopefully you see like why it's essentially performing the same operation as binary search when you do it this way. But the process of searching through a binary search tree is like you're always starting at the root, and you're always checking the value there. You might get lucky, like, oh, I'm looking for 5. And you're like, yeah, it's there. Let's say true or false if it's there or not there in the tree. If it's not the thing you're looking for, you either go left or right, depending on the value you see there. Like, is it bigger or is it smaller, right? So if you start going left, that means you were looking for something smaller than the root's value. And if you go right, you're looking for something larger. And it's always relative, right? It's always relative to that. And you can always keep playing that game because of the binary search tree property. You get to the next node. This is essentially the root of a smaller tree, and you play the game all over. All right, so that's how that works. You just repeat that until at the new subtree you're at, until you either find the thing you're looking for or you find null, which means that it just wasn't there. So here, graphically, let's search for 42. Knowing that we were given a binary search tree. All right, I'm at the root. I look at the root node, 5, compare it to the 42. Oh no, I'm looking for something bigger, which means that if it's there at all, it must be to the right of me. All right, so I'm going to go down the right subtree and get to the 10 node now. All right, so here I am now. I'm at the 10 node, and again, compared to the 42 I'm looking for, this is going to be a loop, right? Is it the thing? No. The thing I'm looking for is bigger, which means that if it's anywhere at all, it must be to the right of me. So I'm going to go right again. Instead of like n equals n arrow next, n equals n arrow right. And then now I'm at the 42 node. Hey, that's what I was looking for. Great. All right, so I find it, and it works out. If I'm looking for something that's not there, you'll eventually get to a null pointer. Like that's where it would have been. Let's search for 7. So it's starting at the root, 5 versus 7. 7's bigger, so I'll go right. Now I'm at the 10 node. Oh no. Well, I'm looking for 7. 7's smaller than 10, so if it's anywhere, it must be to the left. So it'll try going left, and then what's 10's left node? Left child, it's a pointer to nothing, right? It's the null pointer. We'll get to here, get to nullness, and don't dereference it, and we'll just notice that it's not there, okay? So that is, that just means that it wasn't there at all, because that's where it would have been if it was inserted, right? If it was there at all, that's where it would appear. So that actually leads us to an algorithm for insertion, which is kind of cool. But that's how you search. Questions about that? So yeah, let's write a function that does that. Let's make a tree, and we'll write a search function. I think that would be fun. And we will go from there. And that, I think, is everything I wanted to do today. Yeah, so let me make this exact tree, this binary search tree, and that'll be that. I would like to make a new file, call it BSTs. And let's just not deal with parents right now. I don't want to set those. And I will make several nodes now. I'm going to make a 5 node, a 3 node, a 10. I still need a 4 node. I need a 10 node. I need a 1, a 4, 10, 1, 4, and then 42. Oh, I could have kept the 42, darn. 1, 4, and 42. Put it in some order, though. So, all right, 5's data is 5. 3's data is 3, yes. 42's at the bottom now. 10's data is 10. 1, 4, and 42. Yeah. I think that's all of them. 1, 2, 3, 4. There's 6 of them. Yes, in order. Cool. So there's all the data for those nodes. I've forgotten about parent pointers. I'm not going to deal with parent pointers for this example. We don't need them anyway. We're just always going down, never back up. And then we need lefts and rights. Yay. So let's do... I don't want to deal with any of this. So let's do this. Get rid of the parents as well. So let's say, all right, 5's left is 3, 5's right is 10. 3 node, 5's right is the 10 node. 3's left is 1, 3's right is 4. Ten's left is nothing. 10's right is 42. So null, to mean nothing. 10's right is 42. And then everybody else is a leaf. The 1, the 4, the 42, they are leaves, so they're left and right. Both of them, both left and right for those nodes are null. So, for example, 1 has no left or right child. 1's left is the same as 1's right is nothing. That's for 1, for 4, and for 42. And then the root of this tree is the 5 node. Yay, I think we did it. So I'll get rid of these. Any questions about how I built this tree? All right, so I hope I did it right. We'll find out real quick. Now I want to make a search function, and it'll just give back true or false if it finds the thing or doesn't find the thing. So search is those things, and yeah, let's try to figure this out. Let's call it a few times just to get practice. Let's search for 42, let's search for 7. So let's see how. Searching, starting from the root for the 42, and for 7. And so we want to see true or 1 and false 0 for those. Well, let's see. Let's see what we get. Yeah. Okay. So here's the algorithm in word form. Let's turn it into code. So, all right, we always want to start at the root and like use that as a pointer, as a window to where we're looking right now. I'll call that like, I don't know, call it n or something. And n's going to like start there, move to there as we move down the tree. So like, let's have a node that lets us move around, just like we did for linked list stuff. So I'll have a little pointer that starts at the root, okay? So I'll say tree node star n equals the root of that tree that I was given that I want to search through. And then I'll go from there. So start our node pointer at the root. And then as long as I can, as long as I have a node that I can actually look at and compare its key to something, I would like to do that, right? I want to do the process of like, look at the value inside that current node and then make a decision of like, either I found it or I need to go left or right, okay? So what it means to have a node to actually look at right now is that it's not null yet. So while n is not null, it's a valid node to look through. Does that make sense? It's something concrete, like at the start, 5 is of course a real pointer somewhere on the heap. It's not null yet. But if you don't find something, eventually you'll hit null, and then we don't want to dereference that and try to look at the value, the key inside of nullness. That's disgusting, right? So if it's not null, that means we hit the body, and that means we're allowed to dereference that endpoint. All right, so that means that we can look at now n's data and not have to worry. And then we want to see if we need to go left or right, depending on what we find there. So yeah. So now we do a comparison. So if let's see, we've always got a key that I'm looking for, a value that I really care about. If it's smaller than the thing I see at n's data, that means go left. So I'm looking for, I don't know, let's say I'm looking for 1 and I see 5, right? Because I start at the root. I'm looking for 1 and I see 5, that means I better go to the left. My n better change to be n's left, because it's like the 3 node will eventually get me to the 1 node. So go left if the thing you're looking for is smaller, because that's how it's stored in the tree, right? If it's a binary search tree, smaller things are to the left of you. So n equals n arrow left. That would move n, if I was looking for 1, and was here, it would move it to there. See that? And we get closer. If that, the opposite could be true, like if the key we're looking for is bigger, else if the key is bigger than n's data, then I want to go right. N equals n arrow right, and that's what's going to happen when we search for 42. Like if I'm at 5, I'm looking for 42, I compare and I see that, oh yeah, 42 is way bigger than the 5 I see right here at this current node, but this is n. Then I want to say n equals n arrow right, because the 10 node is closer, right? That's the subtree where the 42 really is. I want to keep going, right? And eventually you'll go right again, right, to get to this one. And then you'll finally find it. So yeah, if it's not too small, it's not too big, it was just right. Otherwise, it was there and you found it. Yeah? So our job is to just a silly function to return true or false. Is it there or is it not there? So we'll return true if we find it, and that's us finding it. If this loop ever stops, that means we've gotten to, like our n is pointing to nowhere. We've gotten to like we made our way to a leaf or like a node that didn't have that child. Like you're searching for 7, you start here, then go here, then go here. And that just means, oh, there is no 7. It would have been there, but we hit null. It was supposed to be the left of 10 if it was anywhere, but it was not. So that means if this loop stopped and is invalid, we would have found it if it was there, but we didn't, so it does not exist if we got here. And must be a null pointer. It's the only way we would have broken out of that loop. So we didn't find the key. So sad. So we'll return false to indicate that. And that, all on one screen, nice, is the algorithm. Are there any questions about it? You see it? And it should work if I didn't make any mistakes. Making it or the tree. Boop. So yes, we see that the 42 node, yes, it's there, it finds that, and the 7 node, it finds that it's not there. Okay? So that's pretty neat, and I think that is what I wanted to say. Any questions about that before we analyze the complexity of that algorithm? All right, let's do it. So let me make a simpler tree, just so I can draw stuff. Let's get back to blue. And this will be the last thing we do. So 7, 42 can be to the right. I can put a 4 here. Could not put an 8 here. I hope you see. And then here is the root of my tree. The root of the tree, let's say, is 7. All right, that's the whole tree. And so, I don't know. Let's figure out, I guess space complexity, that's pretty easy to figure out. What are we doing for searching this? Like we're given the tree, you don't count that. When you're calling this function, it's taking 2 things, a pointer, 8 bytes on a 64-bit architecture, and a key value, that's 4 more bytes, that's 12 bytes total. And then it's also using 1 extra pointer variable, so plus 8 more bytes. No matter what you're looking for or how big your tree is, does everybody see how that is constant space complexity? We're not saying new anywhere. We're making a few like we have the parameters, those count, like special kinds of variables. And here's another variable that we're using. It may take a while if it's a big tree, but it's constant space for sure. You see that? Just a few variables. So that is it's just the size of all the variables we need to perform the search with. Just like 3 values. You got a pointer, another pointer, right? First pointer, second pointer, and then this int value, which is 4 bytes. So that's, what is that, 16? 20 bytes. 20 bytes to do this process, more or less. So that's constant, no matter what, no matter how big your tree is. That's great, okay? The time complexity gets interesting. So think about the time complexity as like, for worst case, of course, that's what we care about in this class. The worst case time complexity is you've moved down as many nodes as you could possibly move down, right? And maybe you still didn't find it. That would be the worst case, right? You followed as many edges as you needed to, and you were looking for something that just wasn't there. You went even further, right? So maybe like looking for 5, for example, in this tree, that would lead to the worst case complexity because you go down the height of the tree, yeah? Like you start your endpoint there, 5, okay, 5 is smaller than 7, so I'll do that. Oh, 5 is bigger than 3, so I'll go right and do that. Oh, 5 is bigger than 4, so I'll go right. And then I'll get to nothing, and oh no, it wasn't there. So I went down the height of the tree plus 1, kind of. Does that make sense? That's the worst case. And that leads to a time complexity, right? Because what are you doing at each level, right? You're working your way down through a tree. You are doing constant work at each node you see along the way. Does that make sense? Like this inner thing is just an if-else, like it's constant time per node you're looking at. Is that clear? Any questions about that? Because that's important. Like at each node, at each end node you're looking at, you're doing some just constant work. You're doing some comparisons, maybe doing some dereferences, changing the values of variables around that. It's constant work for this body of this loop, yes. Constant work per node you're looking at. And now the question is then how many nodes you're looking at in the worst case. So you're going down the height of the tree, number of edges, plus 1 to get to null maybe. And then at each node, you're doing constant work. And so let's say that h, let's use a variable because we're not sure, h is the height of the tree. Like n is also how many nodes you have. So I'm not sure what the height of the tree is, but we can use a variable for that for now. The worst case, you're going down the max number of edges, you're doing constant work at each edge. So you're going down h nodes, essentially. Is it on the order of h nodes in the worst case, doing constant work at each, and so it's O of h times O of 1. And that leads to an analysis where the amount of time it takes in the worst case for search depends on the height of the tree. It is essentially the height of the tree. It's O of h time complexity. Does that make sense? Are there questions about that? It's a new variable, but like that's the answer, right? It's whatever the height of the tree was. In the worst case, like you can go down that far and no further. So you'd end up with null after that. Any questions about that? It's a little weird. There are different schools of thought. This is how I want to teach it to you for now. Your book is going to say different things, potentially. This is how I want to teach it to you now. Because you can think about also, like, n is the number of nodes in this tree, right? You can think about a disgustingly unbalanced tree that looks like this, where the height is the number of nodes. So you could also say O of n is an answer here. But I think it's a useless answer. I think this is a more constructive answer. The height of the tree, because that's really your bottleneck here. All right, because the tree doesn't always look disgusting like that. It looks something like this. Maybe is in between balanced and unbalanced. So I think height is the best starting point for us. We can make that more complex later. Okay, but I think that is a good analysis. So it's constant space, O of h, where h is the height of your tree, time for searching. Okay, I think that is all that I wanted to say. So you got the algorithm now. You can stare at it, make sure you understand it, and ask me lots of questions. But I think that is everything I wanted to say for the day. Are there any questions about this or anything else? All right, so what's that?
Can you put doubles as your keys?
Doubles as your keys? Oh, sure. Yeah, we were talking about you could put a character here. So for sure you can put a double. You just change it to say double data. Is that what you meant?
Yeah.
Yeah, for sure. Honestly, just like for lists, you could have made this templated. Because it should work the same for any type you want to use, yeah? So that's the real answer. It could hold anything at all. It should be, it should not care about the type involved. Yeah. Other questions? All right, so that's where I'd like to stop for the lecture. We will have more to talk about later with trees, but that's all I wanted to say for now. I've apparently stopped that. Please do attendance if you have not already. I'll stop that in a minute, and I believe that is all that I wanted to do if I remember right. Yeah, we'll have a new lab, but we'll talk about that one next time.